Hey guys, what's up? Welcome to my video. Today we're talking about the software that I made specifically to visualize Darrieus turbine data, which is DRAFA, the Darrieus Rotor Aerodynamic Force Analysis software. It is designed specifically for Darrieus turbines to take your data and produce insights without you having to code anything at all in an instant. So without further ado, let's get started. Okay, so the first thing that you gotta do if you want to use the software is to prepare your data. DRAFA is used to analyze detailed single blade data. It does not matter if your turbine has 3, 5, 6, 7, 8, 9, 10 blades, it will analyze data from a single blade at a single time. Which means that this is the format of the data that you need to upload into DRAFA. You'll have an Excel sheet and you'll upload the time, the tip speed ratio, the lift coefficient, the drag coefficient, angle of attack, the thrust coefficient, the theta, the azimuthal location of the blade, the Reynolds number, the average torque, total blade velocity, and the turbine inflow velocity. Typically, this last column here, the turbine inflow velocity, for steady state cases, it's just a constant all the way throughout, right? The great thing about this software is that you can easily grab data from other people's papers using web plot digitizer perhaps, and then you can actually put it into this format and upload it into DRAFA to compare your results directly with their results. If you want a sample of this Excel sheet, you can easily go to my drive over here. I probably shared it with you. If you're watching this video, you can grab the data from this sample data folder over here, SIS data. This is the data that I published in Physics of Fluids. Once you start up the software, the first thing that you gotta do is to load the data. The next thing that you can do is to plot the tip speed ratio, which all you have to do is just click on this. This data that I published in Physics of Fluids was to study a self-starting Darrieus turbine. So the data has many turbine revolutions, about 23, 27 or so. Okay. So the first thing that I wanted to do was to plot the tip speed ratio so that I can look at places where it's not performing so well. Moving on to the second module of this software is to plot the coefficients of lift, drag, and thrust against the azimuthal location in this software. So let's say, for example, I want to plot the first cycle. I would just key in the number 1 over here, okay? And if we take a look at this plot, the left-hand y-axis is the magnitude, the x-axis is the theta, and the right-hand y-axis is the angle of attack, okay? So the lift coefficient is shown by the blue line over here. The red is shown by the drag is shown by the red, and the thrust is shown by the black. Okay, the data is read from left to right, which means that the turbine blade starts at 0 degrees azimuthal location. As it rotates, the data is recorded in this manner. You can also observe the angle of attack reaches all the way from 0 to 180 degrees and goes all the way down to minus 180 degrees as well. If you want to plot the stall angles, you can simply just key in the numbers over here and just plot, right? You can show the quadrants, you can show the legend, okay? You can also plot the pitch angle if you inputted it into your data file, okay? The next functionality that I'm gonna be showing you guys is to plot these coefficients of lift, drag, and thrust against the angle of attack to really dig deep into the aerodynamic phenomena over here. So let's say I want to plot those quantities for, let's say, perhaps the 8th cycle, okay? This is a plot of the lift, the drag, and the thrust coefficients against the angle of attack. And these lines here represent those of the stall angles. One of the key things that I mentioned about this software is that it's able to detect dynamic stalls. How? Well, we can see that the blade, as it rotates 360 degrees about the central axis, it's actually exceeding the static stall angle over here. Now let me pose a question to you guys. How do we isolate the effects of unsteady aerodynamics of the turbine? And the answer to this is simple. Imagine if we had a turbine blade, we placed it at 0 degrees, okay, and we blow the inflow and we calculate the lift, drag, and thrust, and then we manually rotate the air forward by, let's say, 5 degrees. We blow the inflow and we get the lift, drag, and thrust, and we keep doing that over and over again. In this way, we can actually get rid of the unsteady part of the blade behavior which means that the result that we will get if we kept doing this and we rotated the blade 360 degrees around the central axis, we would get sort of like a steady, a quasi-static behavior of the blade. However, we need to have two polars. The first polar is for a lower Reynolds number of, let's say, perhaps 3000. The second polar is for a Reynolds number of, near the maximum Reynolds number that the turbine blade will encounter, which is about 130,000. And we need these two polars, and then we can interpolate between the two polars to produce sort of like a quasi-static polar that is applicable specifically for the turbine data that you are working on. Long story short, all you have to do is click this load polar, this pop-up will come up, and just click, and then I'm going to click on ignore unsteady aerodynamics, and I'm just going to compute. Okay, so when it's done, it will tell you it's done. We just click OK, and we close this. The next thing we're going to do is click on this show steady aerodynamics. What we're observing here is a plot of the dynamic and the static coefficients that we're interested in taking a look at. So if, let's say, I want to take a look at the static lift versus the dynamic lift, I would click in line properties. I can actually hide all of the. This plot compares the quasi-static lift coefficient that I mentioned just now in a scenario where we were to actually take the turbine blade and to rotate it 360 degrees manually in a quasi-static fashion, as compared to the actual turbine data which you uploaded, where the turbine is rotating 360 degrees by itself. Okay, so the difference between the magnitudes of the lift at these two different points, let's say at 10 degrees over here, that is the effect of unsteady aerodynamics. This is a very powerful tool within DRAFA which allows you to isolate the effects of unsteady aerodynamics within the turbine data that you have provided. Now moving on to the next module, which is the quadrant breakdown module. It allows us to plot the contribution of the blade to the torque being generated with respect to the quadrant that it is in. So what do I mean by that? Let me just plot it out and show you. This plot here shows the windward, the upwind, the leeward, and the downwind quadrants if the inflow is coming from the left hand side. What we have is that on this windward plot over here, the left hand y-axis shows the torque contribution, the x-axis shows the cycle number. Okay, and we can see that the contribution of torque we can see that the blade generates not so much torque for this quadrant. However, if we take a look at the upwind quadrant, we can see that, wow, the blade actually generates most of the torque in this quadrant. If you want deeper insights, all you have to do is click on this lift drag breakdown option over here and click the plot. Click this button again, and the software is gonna plot the lift drag contribution for you. The objective of this quadrant breakdown module is to effectively visualize the poorly performing quadrants of your rotor so that you can perhaps implement design changes into that specific quadrant. A key functionality of this DRAFA software is the ability to plot the vectors of lift, drag, thrust, and the angle of attack all at once of that blade as it rotates about the central axis. What do I mean by this? Let me just quickly plot it out and you can see. Okay, I have enabled the legend and the scale at the same time. The green arrow is actually the relative velocity vector. However, it can also represent the angle of attack. The blue arrow is the lift coefficient, the red is the drag, and the black is the thrust vector. If you would like to begin the plotting on the left side, you can just click on this option over here. And it's actually just going to rotate the plot towards the left. So it actually shifted it counterclockwise by 90 degrees. And we can do the same if we want to start the plot at the bottom or on the right. I can also show the quadrants, I can show the legend, I can show the grid lines if I want to, and I can also reverse the angle of attack. Another important functionality is the ability to be able to reverse the direction of the plot. Well, what is that exactly? if, let's say right now, the turbine vector diagram shows that it's rotating counterclockwise, and I actually want to rotate clockwise instead, I just click on this button here, and tada, now it's rotating clockwise. I can zoom in, I can just adjust this zoom, this slider, that's too close. If I want to zoom out, I can do that. Okay, I can reset the value and replot. And last but not least, I can also adjust the range of the vector diagrams that I'm plotting. So I would also recommend that you plot the vector diagrams on this by clicking on this MATLAB plot over here, and it will plot out the vectors for you. So here I can click and see, okay, this is the vector diagram at theta equals to 0. This is the vector diagram at theta equals to 40. This is the vector diagram at theta equals to 80. What I can do is that I can adjust the density of the vector diagram by going back to the software. And let's say, I know that according to this text over here, the minimum is 1. The TVD range, the minimum is 1. And the maximum is 180, okay? And in between, this is the range. So maybe I want to double that density. I'm going to change from 20 to 10. And I'm going to come out, and it's going to plot out an even denser turbine vector diagram plot. And instead of just plotting, 0, 40, 80, now it's going to plot 0, 20, 40, 60, 80, so on and so forth. So you can play around with this configuration to plot any number of vectors that you want. In my one pager, I actually showed you guys that you can overlay these vector diagrams directly on top of your flow field. How can you do that? Let me show you exactly how. Okay, so I'm plotting my vector diagram now, and I'm gonna reduce the density because let's say I want to plot the vectors for perhaps a very specific azimuthal location, maybe 60 degrees, and I only want to plot that one. So I'm just gonna change this to 1, 30, and 30. Now, all I have to do is just save as. I'm gonna save this as an SVG file, PowerPoint slide, okay? I'm gonna crop, and then I'm gonna set the graphics as graphics fill, no fill. So it's gonna make it completely transparent, okay? Then after that, I can rotate it as I like, I can rotate it so that it fits as I like and overlay it nicely. If you probably run into this problem at first, the vectors are too big, all you have to do is just go back to the software and just click on scale vectors, and you can scale the vectors as you like. Ta-da! The vector has reduced its size by, reduced to 10% of its original size. So that's how you use DRAFA. I hope you guys found this really useful and you guys make full use of this software. If you have any doubts or questions or any feedback, you could just click on this button over here. It's going to lead you to a Google form on Google Chrome, and here you can write your email address and you can just tell me what your thoughts are, any feedback, how to make the software better, or any feature that you would like implemented. Just let me know. I'm open to hearing anything. Thank you for watching, guys.